All right, let's talk about what information should be on a it's easy for you to say, a motor nameplate. And as it says, nameplate is a description of the manufacturer listing specific information about the motor characteristics. Nema standards and all the other standards say that every motor has to have a nameplate and it's got to give certain information. And generally it'll have some model number from the manufacturer, which isn't too significant, because the main thing you want to be able to do is replace the motor with somebody else's motor. Fairly often, let's say it's a ball door motor that's burned up and you're on a job site, you happen to be out in the desert near Las Vegas, and you run to the local wholesale house, the nearest one in Vegas, and you find out they don't carry ball door motors at all. And what do? What you do is you find one that has the same horsepower, the same voltage, and the same current demands, more or less. If it has a lower current demand, that's okay. That just means it's more efficient. And the same frame size. That's why we say that we don't have a case on the motor, we have a frame, because it's classified by Nema frame size. Okay, so the manufacturer's name, model, and serial number has got to be on it. The motor type identifies the type of motor, generally describing the starting method, including if it's a DC motor, whether it's shunt or series, and whether it's compound wound, permanent magnet, universal, whatever it might be. Single phase motors, it's going to indicate whether it's split phase, shaded pole, permanent split capacitor. We use PSC motors in the lab, by the way. And capacitor start, capacitor run, or universal. In three-phase motors, it'll tell you whether it's a squirrel cage induction motor, a wound rotor motor, or a synchronous reluctance type motor. Synchronous or reluctance motor. All right. Also, it will tell you about the enclosure type. We were just talking about hazardous locations moments ago, before class really started, and we were talking about some hazardous locations have special enclosure requirements, such that if an area is in a Class 1 Division 1 area, which means that it's got a hazardous or got an explosive or flammable vapor that is always there. It's always there. That's a Class 1 Division 1 area. That means that if that motor throws out a spark into the open air, you might have an explosion or a fire. Very ungood things happen. So we don't want to have that. We want to know what kind of enclosure is required for different areas. And we're going to talk about enclosures later, all the different classifications. But we just want to know that right now that the motor nameplate has got to give you some information about that. Okay, and these are the motor enclosure ratings, kind of the general groups. Take a look at that on the website. We're looking at information from the Moodle website for this class, so you can look this stuff up and look it up anytime you want. Now, a very important thing is it'll tell you the Nema frame size designation. Okay? And it's assigned a series of standardized numbers and letters to describe various dimensions and mounting types of motor frames. When changing a motor, selecting the same frame size regardless of manufacturer ensures the mounting mechanism and hold positions will match. Isn't that wonderful? That makes it so that you go to the wholesale house in Vegas, they don't have a ball door motor. If you get the same horsepower, the same voltage, the same current, and the same frame size, it's going to drop right in, and you'll be able to replace it without a problem. That's a very good thing. As a general rule, as the frame size goes up, the general size. And the frame size is really, we're going to talk about this in a minute, but it's really the diameter of the motor, assuming that it's a round motor. There are a lot of motors the same horsepower and size, built with different frame sizes, so they can be mounted in very different locations. So the frame size designations, it'll have a prefix, frame number, and a suffix. For instance, EF56C means, what does that mean? The EF in the frame size is the manufacturer's indication that something about high efficiency. The frame size number is a 2-digit number, generally speaking. And 2 digits indicates a fractional horsepower motor, less than 1 horsepower. So the nameplate displays 2-digit frame number. The number is the distance from the center of the drive shaft to the center bottom of the mount in 1/16 of an inch. You might want to highlight that or write it down. So the frame number is the center out. It's the radius. The radius in 1/16 of an inch. So this example of 56, that's 56/16. How many inches is that? I want to hit pause while everybody thinks about that for a minute and pulls out their calculator. So let me find the, I don't see my recorder. So 56/16 is, one more time. 56 divided by 16 is what? 3.5. Okay, 3.5. That means that this motor has a radius of 3.5 inches. That means it's a 7-inch diameter motor, right? All righty. So now this frame size is becoming very important, right? Because it's going to help you replace a motor when you can't get the exact same one. 3-digit frame size means that it's greater than 1 horsepower and greater than what size? Oh, we could figure that out. Okay, so we have in the example in our note from the manufacturers, we have EF145C. What is 145 divided by 16? Oh, we don't want to divide by 16. We want to divide by 4. Why is that? No. It says 14 divided by 4. How did we get 14? Because the 3-digit frame size gives the 2 digits. Divide the first 2 digits by 4 to calculate the distance from the center of the drive shaft to the center bottom of the mount. So in other words, the first 2 are still going to be divided by something. In this case, 1/4 of an inch. So the first 2 digits are now 1/4 of an inch instead of 1/16. So if we have a 3-digit number, the first 2 are 1/4 of an inch. So 14 quarters is 3.5 inches. So in other words, this motor is 3.5 inches in radius. In other words, it's also a 7-inch diameter motor, but it's telling us that there are bolt holes that are 5 inches apart. That's what that last number means. The third digits indicate the distance between the mounting holes parallel to the base. Parallel to the base. Say again? We'll leave that in. No, if you've got 3 numbers, the first 2 digits are still the radius from the center of the shaft down to the plate. So, except that it means it's 1/4 of an inch, not 1/16 of an inch. Okay. Okay. Motors that have a letter following the T indicate different things. S indicates Nema standard short shaft for belt-driven loads. U would indicate motor manufactured prior to 1965, in other words, old. Y indicates non-Nema standard mount, which may be special base. flange or frame, so on and so on. Z indicates non-NEMA standard shaft. And so all these indicators are important to you. Where are you going to find that information? If you're at the wholesale house, you can ask for a sheet that describes these indicator letters, or you could go back to this sheet, print it out, save it, whatever. But by then you'll have lost it, I'm sure. And then there are insulation classes. Types of insulation based on motor depends on the operating temperature of the motor. In other words, we're temperature rating or the insulation of the wires. And they're not given in the things that you would normally expect. They're given in A, B, C, D, and so on. Class A insulation, standard insulation used on older U-frame motors between 1952 and 1964. T-frame produced 64, used Class B insulation, and so on. Okay. Now, insulation temperature charts use to select insulation that will provide dependable motor life. A motor operating at 100 degrees centigrade will have an estimated life of 300 hours with Class A insulation, 1,800 hours, Class B, 8,500 hours, Class F, and tens of thousands of hours with Class H. Also, the amount of temperature above 30 degrees centigrade will affect the life of the motor also. Horsepower ratings. The thing you're going to look at first on most motors is the horsepower rating. The full load output of the shaft of the motor can produce without reducing its operational life. And if it's higher than 100%, it'll have a service factor indicating that you may overload it for short periods of time. We'll come to that later. So the NEMA standard horsepower ratings, 1 through 4,000 horsepower, are these right here in this chart. Take a glance at that and notice that they go all the way up to 4,000 horsepower. That is a big motor. I'm just thinking, what is the frame size on a 4,000 horsepower motor? Okay, how do you indicate? Well, never mind. Power ratings should be a continuous brake horsepower. Sometimes they'll have different indications, like a European motor might be rated in kW, which is supposedly thousands of watts, and watts is pure power. The speed that it turns at is often important to you. Sometimes it's not. Sometimes it's very important. Okay, normal operating speeds for 60 cycles and 50 cycle Hertz may depend on the number of poles in the motor stator. A lot of motors are dual speed. Okay, then we have speed classifications: constant speed, multi-speed, variable speed, and adjustable speed. And then one of the most important things is duty rating. Motors are classified according to the length of time expected to operate under full load, and continuous duty, as according to the National Electrical Code, is anything over 3 hours. Anything over 3 hours is continuous duty. Intermittent duty, therefore, has to be less than that. If you don't know, what do you assume it is? If you don't know whether it's going to be operated 100% of the time, 10% of the time, if you have no idea, assume that it's continuous duty. Phases, generally speaking, you only see single phase and 3-phase in DC. There are 2-phase motors, but they're so unusual, I don't think it's worth talking about anymore. You know the advantage of 3-phase motors. They They're more powerful than a single phase for the same size and current. Okay, rated voltage, single phase motors can go up to 230, 460. Remember that 2 hot wires is still single phase. Okay, 2 hot wires, like when we do the Edison 3-wire, that is still, even though we've got 120, 120, phase A, phase B, and 240 across it, that's still a single phase 240 because it's coming from 2 single phase supplies. 3-phase motors up to 125 horsepower, above 125 horsepower. And nominal system voltage and actual motor voltage. Nominal voltage is kind of the general classification. The actual nameplate voltage might be slightly different from that. Generally speaking, 120 volt nominal voltage means that it's actually 115 volt. The motor's expecting to see 115 volts, but anywhere you hook it up, it's going to be a little more or a little less than 115, right? And as long as it's not too much low, we're okay with that. If it's more than 5% low, it will cut the motor's life in half. Let me say that again. When the voltage is low, the voltage supplied to a motor is more than 5% below its actual nameplate voltage, it will cut its life in half. And remember that sometimes that will mean that you're going to wind up buying a new motor instead of the manufacturer supplying the motor. Okay, hertz or frequency. You know that everything here in the United States, generally speaking, is either 60 hertz or 400 hertz for very specialized military applications. And if you go to Europe and a few other places, you might see 50 hertz. The current is known as the FLA, full load amperage, okay, or full load current. Please don't use the phrase running load amps or running current. There are some old terms that create confusion between some other parts that we're not going to talk about at the moment. But just take my word for this. Use the phrase FLA, full load amperage. FLA, that's the current that it will run at, producing the maximum power that the motor is rated for. Here we have service factor finally. It's the amount of overload over nameplate rated power the motor can tolerate continuously at rated speed and voltage without reducing its life. So what are they saying if a motor is rated 1.25? That means that you could run it at 125% of its total FLA on a continuous basis. It's better not to make it a continuous basis if you're overloading it. If you're overloading it all the time, go to a bigger motor. Okay? Service factor greater than 1 allows a margin for peak horsepower demand without selecting the next larger motor. Below 1, big difference. Actually, it won't be below 1. It'll be a service factor of 1. That means that do not overload this motor at all, ever. If you do, you're going to cut its life down. Okay? So what do we do when we select motor overload heaters? I know we're not to that point yet, but when we get there, if a motor has a service factor rating of 1.0, the overload heaters are actually going to be selected at about 90% of the full load amperage because we don't want it being overloaded at all. Okay, so generally you'll see 1.0 fairly commonly, or 1.15 or 1.25. Those are very common ratings. And really and truly, if you buy quality motors, you're generally going to see 1.15 or 1.25. If you're buying the cheapest motor made on the market from any country in the world, you're probably going to see service factors of 1.0. And why are those motors cheaper? Because they use actually less copper to build the motor. But that's a whole different discussion. All right. Design code. What is a design code? When a motor is started with a full load current, in other words, an across-the-line starter, and that's mainly what we're studying in this class. An across-the-line starter is called a full load starter. In other words, it slams the whole current to it immediately. None of this ramping up with a variable speed drive and taking the load up a little bit at a time. It's going to slam it to it and just take off as hard as we can, right? Okay, well that is an across-the-line starter. And for a moment, it's going to have an inrush of many times its standard full load amperage, up to 6 or 8 times its standard full load current, because at first there's no inductance, so the resistance through the motor is only the wire resistance of the windings, not the inductive reactance. So for a moment the current will be very high, and as the magnetic field builds up, it'll start reducing the current flow back to its FLA. Code letter of the motors are an indication of the locked rotor current. Locked rotor current is that current that it starts at when it's started on across the line power, meaning that if it's 6 times the FLA, 6 times 100 amps is 600 amps, right? So the locked rotor current for that motor might be 600 amps. And that's a different chart, and it's in the code book. Okay? And here we have the code letters and what they mean. The kVA inrush current per horsepower is a range that is related to the code letter. So you can kind of tell whether the equipment you're selecting is going to start the motor or not if you know the code letter of the motor. And it's right on the nameplate. Now, power factor, it would be nice if they're stamped on every motor, but a lot of motors it's missing. New motors is supposed to have it on there, and it is the electrical efficiency of the motor itself. The electrical efficiency, not the total efficiency, because it does not include friction and things like that. Then often it will show you a connection diagram. It won't look like this, but it'll say something like on a 3-phase 2 dual voltage motor, it'll show you how to hook it up to the high voltage and the low voltage. And it'll show you, for instance, 1, 2, 3 is connected to line 1, 2, 3, and 4 is connected to 7, and 5 is connected to 8, and 6 is connected to 9, and so on, things like that. So often it'll give you a connection diagram, or it'll tell you on a single phase, often it'll show you how to make it run forward or how to make it run reverse. The ambient temperature is fairly important. On a motor nameplate provides the maximum ambient temperature the motor should be operated within. In general, the maximum ambient temperature for motors is 40 degrees centigrade or 140 degrees Fahrenheit. And that means it can run above 40 degrees or 144 degrees above the ambient temperature without doing any damage to the motor. So if it's 104 degrees above an 80-degree room, it's 184 degrees on that motor, right? Outside surface of the motor. Does that indicate that you might not want to touch that motor? 184 degrees, think about that. Boiling is 212. It's just short of boiling. If you're going to touch a motor that's running at 184 degrees, you might want to be wearing your gloves. Okay, so read over all this material. Temperature rise. Now this is an important factor. It's the increase in the internal temperature as it operates due to the current flowing through the windings. The ambient temperature plus the temperature rise, the max temperature which the motor should operate, and that's what I was just talking about a minute ago. If it's 80 degrees Fahrenheit and it's got a 70 degree centigrade rise, that means it's going to run 70 degrees centigrade above that. Now that motor, if it's got a 70 degree, that's very unusual. Usually it's 30 or 40 degrees. And 40 degrees alone is 140 degrees Fahrenheit, and that's where we get our 184 degrees operating temperature in an 80 degree room. What if that's a 100 degree room and it's a 104 degree rise? 204 degrees, that's very close to boiling, isn't it? Pretty hot. Okay, and that is not, sometimes you'll get a call from some unsophisticated customer that says, hey, I think this motor is running way too hot. And you say, hey, do me a favor, go read the temperature rise on the motor for me and come back and tell me what that is. And he'll get off the phone and say, I'll call you back. And he calls you back and says 50 degrees centigrade rise. And what's the temperature in the room? It's about 95. Okay. Let's convert that 50 degrees rise in centigrade to Fahrenheit. What's 50 degrees centigrade converted to Fahrenheit? Anybody? 122 degrees plus 95 degrees is above boiling temperature, isn't it? Well, it's right below it, 217 degrees, just below boiling. And no more than you would stick your hand in boiling water would you put your hand on a motor. So when this customer calls you and says, hey, I think this motor's running way too hot, I touched it and burned my finger. And what are you going to tell them? Okay, well, that's not a problem. Don't touch it. It's okay for it to run at 217 degrees. That temperature rise is how much it's allowed to run above ambient temperature. So if it goes up to 100 degrees in that room, definitely don't touch that motor because it's going to be above boiling temperature of water. Okay, so it's unlikely that you'll have that discussion with most customers because generally they don't go out and touch the motors themselves. They have maintenance supervisors that know that these motors run hot and they're not going to go touch them with ungloved hands, so it's not a problem. Some motors have thermal protection, and really, we don't care about that. I mean, theoretically we do, but let's say that you're going to put in a motor and you're going to assume the thermal protection. Now, this is an old used motor that the owner of the company has given you, and he says, I want these 5 motors put in this room, running these 4 machines, and here's the 5 motors, and one of them looks all old beat up motor, and it has thermal protection in it, and you assume that you're not going to need to put in overload heaters in that motor starter. It's a bad assumption, okay? Because if that thermal protection is not functioning properly and that motor burns up, you get to buy a new one because you decided that you didn't need to protect it with overload protection. So it was your decision that caused that motor to go bad because and generally speaking, it's very difficult to test an internal overload device. So generally speaking, you're going to cover your posterior by using overload protection, whether it's required or not. Okay? I don't care that it's got thermal protection built in. That's nice. We're going to put overload heaters in the starting system, and if it gets overloaded, we're going to shut it down. And we don't care whether the overload internal device works or not. If it does, that's nice. If it doesn't, we're still going to protect the motor. Okay, efficiency. In the past, the efficiency was not in the nameplate. It's the ratio of mechanical power output, the motor can produce compared to the electrical power input. The VAs compared to the watts, right? That's efficiency. That's not efficiency, that's power factor. Okay, most motors operate near the maximum efficiency at rated load. Well, some do. Okay. Motor efficiency varies from the nameplate value depending on the percentage of the rated load applied to the motor. And what they're saying is that at low currents, the motor is not going to be, or low loads, the motor is not going to operate efficiently as it would at full load. So you don't want to use, if you're going to avoid it, you don't want to use a motor that's 10 times bigger than you need to, because it's not operating as efficiently if it's only operating at 10% all the time. A Nema standard MG112 provides instructions for manufacturing and establishing the value of efficiency for a given size and type of motor. And you'll notice that the example here is given at 95.8%. And if you check the incoming power on the codebook motors, you can check motor input power, right, on a single phase motor from the codebook, and its actual horsepower, because the horsepower is the amount of, we can convert that to watts, right? So just from the nameplate, the incoming power, the volt amps, the apparent power, compared to the true power, the horsepower it's supposed to make, you can ballpark its efficiency right out of the bag before you even look at this, right? Because this is not stamped on most motors. And most motors are not anywhere near 95% efficient. Unless you buy a fairly quality motor, it's not going to be up around 95%. If you buy a fairly inexpensive one, its efficiency is going to probably be down around 75%. You're giving away 25% of the energy all the time. Okay, we don't care about special order motors, but please read that. And I think that's the end of our little handout. So I think we're going to stop here for a moment, and we'll, as they say, put this in the can as part 1 of the lecture, because that alone is 32 minutes. So let's stop now, and we'll turn this into a podcast.